series of tutorial videos where we are seeing the different steps that we will follow to define a flexibility workflow in a Scipion using the Scipion Flexibility Hub. In the previous video, we saw how to estimate different conformational landscapes using, for example, Cernic 3D, Scipion, CryoDragon, and so on. So in this video, we will see what kind of analysis we can do in order to improve the reliability of the conformational landscapes we have just estimated. But why do we want to increase the reliability of these estimations? Well, the main problem with any estimation we are doing in CryoEM, this also applies to the case of conformational landscapes, is that for many particles we will be doing the right estimation, but due to the large uncertainty we have in the particles, due to the high levels of noise, CTF, and so on, in many cases we will get a wrong estimation. So what we want is trying to exclude those wrong estimations and keep only the things that we can really trust. And the only way to do that is using a flexibility consensus. This way, what we are trying to do is to analyze the stability of either the same software run several times or different softwares, and then try to move all the conformational landscapes to a common point. And once we are in the common point, what we're going to try to do is to say, okay, which particles are estimated in a similar way, so they have been or they are representing a similar state, and which particles are completely random, which means that they are not estimated properly and we should exclude them. For that, the Scipion Flexibility Hub includes a landscape consensus, which is available in the Flexibility Hub view in the tab Landscape Consensus. You have here the two protocols we want to use in this video, which is the training of the FlexConsensus and the interactive consensus. Let's have a look first at the form of the training protocol. Okay, so this is the form. The form has two different tabs. The first one has to do with the inputs. And here we need to provide the input particles. These input particles are not any input particle in a Scipion, but they are these particles coming out from the estimation of conformational landscape. So they should have flexibility information, like for example, the Cernic coefficients, the latent spaces of CryoDragon, Scipion, and so on. Here you can provide as many particles as you want. So for example, you can provide two sets of particles coming from the same algorithm run twice, or particles coming from different programs, and the consensus will know how to handle them, and internally how to do the consensus for all of these different things. Also, depending on the type of particles you are putting here, it will determine the kind of information you can retrieve from the consensus. So for example, let's say I put here Cernic particles. Then this means that when I want to get my particles back, I can get Cernic particles, that is particles with Cernic coefficients, but I will not be able to get CryoDragon particles. But for example, if I provide Cernic particles and CryoDragon particles, when I create the output, I can decide whether I want to recover the Cernic information or I want to recover the CryoDragon information in order to continue with the flexibility analysis. Then we have the latent space dimension, which usually you put here a number again between 8, 10, 12, something like that, which determines the freedom of the consensus. So in principle, with 10, it should be more than enough freedom to get a right estimation. Then we have another tab, which is the network, that has to do with the architecture and network hyperparameters, like for example, the number of training epochs, the number of images in a batch, which is a useful parameter, as in previous cases, to control or to change when you have memory issues in your GPU. So depending on your GPU requirements, you can increase this value because you have more GPU memory, or if you are running out of it, you can decrease it to, for example, 32 or 16, for example. And then we have the training dataset fraction, which is basically used to split the datasets into training dataset and validation dataset in order to train the network better. Once the protocol finishes, you will see here in the input-output tab of a Scipion that we have the inputs. In this case, we have two runs of the Cernic 3D, one Scipion and one CryoDragon. So this means that I will be able to recover either Cernic particles, Scipion particles, or CryoDragon particles. But you see no output. And this is normal. The training step in this case is just generating all the information needed to posteriorly use the second protocol in the FlexConsensus to recover in an interactive world only those particles that are stable based on the consensus information. Okay, so let's see the next step in the consensus, which is this interactive consensus protocol. In this protocol, You see there is no advanced options available here, so it's a very simple form. You provide some input particles, which is the particles you want to evaluate the stability. This can be either the same particles you use for the training or some other completely different particles. But keep in mind that you need to provide the same kind of information you put into the training. So for example, here I have put Scipion, Scipion, and CryoDragon. So here in principle I should be able to put particles with Scipion information, either the same ones here or some other particles I have made, Scipion particles or CryoDragon particles. But if in the consensus I have only used the Scipion 3D branch and I have not included Scipion or CryoDragon, if you try to put the Scipion particles here, you will get a validation error, saying you cannot run this protocol because I don't know what Scipion particles are, and I don't have that information in the training step. And then you need to provide the FlexConsensus network you trained previously, which if you have a look here, is either one of these protocols of the training FlexConsensus that has all this information that we previously trained in order to do all this interactive consensus step. Once you are happy with your form, you can click on execute, and the first time you run the protocol, you won't get any output either. So your protocol will end up in green, but you will see the inputs, but no outputs. In order to create the outputs, you need to click on Analyze Results. Once you are here, you see here an option saying Error Histogram to display. We should remember that in the training, we are providing different types of particles, and we are computing kind of an stability measure for all these different programs. But the stability measure for Cernic or the stability measure for Scipion, although they will be similar, they can have slight different changes. So what we are doing is trying to match or trying to align all these different stability measurements based on the means of the histograms or by means of the entropy of the histograms that we have computed based on these stability measures for all the different programs. So you have these two different options, and depending on what you want to see, you can use one or the other. What is the difference between the min-match and the entropy match? So in the min-match, we are trying to keep the errors small, because a small error in the entropy consensus means that that particle is very stable. In the case of the entropy match, we are trying to see histograms that are wider, which probably is better to automatically set a better threshold based on the error measurements we have put. But the idea is the same. Smaller errors means that the particles are more stable. Okay, let's have a look at the min-match, for example, and let's display the histogram. This will open this view, which have the errors, which are the stability measure we have taken. And as we said before, the smaller the value, it means that the particles are more stable. Here you have the density of the histogram, so in principle, how many particles have fallen into each bin, right? What you can do here is to use this kind of a slider here to move the threshold to any place you want. And you can see here in the top that the number of particles you're going to get changes. So you can decide interactively if you want to keep a higher number of particles because the number of particles you are getting is very low, or if you have enough particles, if you want to just keep the ones that are very stable. Once you are happy with the number of images and your threshold, if you click on Subset Particles, you will automatically get the output inside the Scipion. You can create as many outputs as you want, so you can set different thresholds and click several times on Subset Particles, and you will register all these outputs inside the Scipion. So later on, you can decide which one you want to use in order to keep on analyzing the flexibility. Once you are happy with your threshold, you will get all these set of particles here that have the same information as the input particles you had. So for example, here I provided 73D particles, which means that if I go to my consensus particles, I am getting the most stable ones that have this Cernic vector here. But I could also, for example, provide as input particles the CryoDragon ones, do the same kind of stability analysis. And now if I open my consensus and we compare to the one of the Cernics, you see that depending on the input you are giving, you are getting either Cernic particles that are very stable based on the consensus, or the CryoDragon particles that are more stable based on the consensus information. So this is a very convenient way to really do the consensus with all the different estimations you have done, but then having a way to go back to the initial information. So if you prefer doing the cernix because you want, for example, to enter into structural models, you can still recover cernix information. Or if you want to use CryoDragon to see how the network is reconstructing different maps, you can also use CryoDragon still. And that's all. With this, you will get all your consensuated polygons based on the different estimations you have done on your landscapes. The problem now is that, as we have seen, what we are getting is either sonic vector or latent space from CryoDragon, from Hetsiren, that has a very, very large dimension. So we cannot really visualize that. And what we want is to interactively be able to explore the landscape and get the different states. So in the next videos, we will see how we can apply this dimensionality with action in the Flexibility Hub, and then how we can use those reduced landscapes to see all these different conformations in real time. Thank you so much for listening.